Hello, I am presenting GenSplat, our approach to efficient camera pose augmentation for view generalized robotic policy learning. The central question is simple. Can a robot remain reliable when the deployment camera moves, without collecting another set of human demonstrations? GenSplat answers this by reconstructing a stable 3D Gaussian scene from sparse, uncalibrated observations in one forward pass. It then renders controlled novel camera views and pairs every rendered image with the original. Expert action. Over the next few minutes, I will explain why this 3D route matters, how the model is trained, and what the real-world experiments reveal. Modern visuomotor policies can perform very well from the camera poses used during training, yet fail after a modest rotation or translation of the camera. A two-dimensional policy often anchors the action to perspective-dependent cues. When the viewpoint changes, object scale, parallax, occlusion, and even the apparent spatial relation between the robot and the target all change. Recollecting demonstrations from every possible deployment view would be expensive and does not scale. Novel view synthesis is an attractive alternative, but the generated image must preserve the underlying metric workspace. If it bends a faucet, changes an occlusion order, or creates floating geometry, the synthetic observation becomes incorrect supervision for a precise physical action. GenSplat begins with several sparse robot observations whose camera poses may be unknown. Each image is encoded into DINOV2 patch tokens. Alternating frame-wise and global self-attention then aggregates the views symmetrically, so the result does not depend on which camera was selected as a reference or on the order of the inputs. A camera decoder predicts each view's rotation and translation, while a point map decoder predicts a dense local three-dimensional coordinate and confidence for every pixel. Transforming those point maps into a shared frame provides the Gaussian centers. A dense prediction head estimates the remaining Gaussian attributes: opacity, rotation, scale, and appearance. After reconstruction, we can sample a target camera transform, render a new observation, and train the downstream policy on the union of original and synthesized data. Pure photometric optimization is not enough in this sparse and uncalibrated setting. It can fit the observed pixels while allowing incorrect geometry, which later appears as floaters, boundary tearing, or topological collapse from unseen views. GenSplat therefore distills geometric knowledge from a pre-trained visual geometry model. Dense point map supervision encourages smooth, metric three-dimensional structure, and relative camera pose supervision constrains rotation on the SO3 manifold and translation. With a robust loss, the total objective combines RGB reconstruction, depth alignment, point map distillation, and camera pose distillation. The qualitative comparison on this slide shows why this matters. GenSplat retains sharp object boundaries and aligned depth and normals, while the final Gaussian scene has a cleaner surface than a depth-supervised feed-forward baseline. For pre-training, the model uses 271,000 images sampled from the Droid dataset, covering a broad range of tasks and environments. Real-world evaluation uses a Franka Research 3 robot and 6 manipulation tasks: picking up a banana, stacking blocks, inserting a ring, placing a can on a shelf, putting blocks into a plate, and stacking cups. The authors train both Pi0 and diffusion policy, demonstrating that the augmentation is not tied to one policy architecture. Every task is evaluated over 30 physical episodes under small, medium, and large camera rotations and translations, with an additional extreme condition in the ablation study. This protocol measures whether the policy genuinely generalizes across camera poses rather than merely matching visual quality. The main result is that geometrically reliable augmentation improves robustness across all 6 tasks in both policy families. Under large camera perturbations, GenSplat reaches an average success rate of 62.2% for Pi0. This is 6.1 percentage points above the strongest feed-forward baseline, AnySplat. While GenSplat synthesizes a frame in only 0.14 seconds. The benefit is even more pronounced for diffusion policy under large shifts. Success increases from 27.78 to 43.33%, a 56% relative gain. Importantly, some apparently plausible augmentation methods hurt the policy. Vista and no-PO-splat fall below the unaugmented baseline, showing that low-quality view synthesis acts as label-preserving visual corruption only in name. In practice, incorrect geometry contaminates the observation to action mapping. The ablation connects the architectural choices to both rendering quality and physical success. Starting from the VGGT-style baseline, permutation equivariant aggregation raises success from 66 to 70% under large shifts and from 30 to 40% under extreme shifts. Adding 3-dimensional prior distillation produces the full model, reaching 74% under large shifts and 46% under extreme shifts. Rendering metrics move in the same direction. PSNR improves from 22.35 to 26.53, while LPIPS decreases from 6.01 to 3.72. The qualitative comparison tells the same story. Diffusion-based methods may hallucinate shape, and Gaussian baselines without strong priors can leave floaters or torn surfaces. GenSplat preserves a smoother, more physically plausible scene that provides cleaner supervision for control. The practical takeaway is that camera generalization can be treated as a data expansion problem. But the expansion must happen in a trustworthy 3-dimensional workspace. GenSplat combines fast pose-free reconstruction, permutation equivariant multi-view reasoning, and geometric distillation to create controlled novel views without new human demonstrations. The experiments show that better 3-dimensional structure is not merely a rendering improvement. It directly translates into more reliable physical execution. If you remember one sentence from this work, it is this: expand the observational manifold, preserve geometry, and a 2-dimensional visuomotor policy becomes much more robust to unseen camera poses.